Could you give us a flavour of the nuclear physics that you did at the time? Because it's a subject everyone knows about, nuclear physics, and you think of things like nuclear power stations.
Nuclear physics in academic research has nothing to do with nuclear power or nuclear weapons. It's about studying the structure of the atomic nucleus, how the protons and neutrons and the constituents of the nucleus, how they all hold together, subject to the rules of quantum mechanics. So, physics undergraduates learn about the Schrödinger equation and solving the Schrödinger equation. Well, that's essentially what you do. You solve the equations of quantum mechanics to work out how the protons and neutrons are arranged. My area was in nuclear reaction theory, which means you study the dynamics of two nuclei hitting each other and working out how they break up, how they bounce off each other, the angular distributions, the cross-sections, and you build in the models to see it, because that's the thing that gets measured. You know, you can't look inside a nucleus. You can measure things like lifetimes of a nucleus, or when it spits out a particle if it's radioactive. But by and large, in nuclear accelerators, just as in particle accelerators, higher energy ones, you're looking at how these things bounce off each other and what's created. So that tells you something about the nucleus in the first place. Usually you have two nuclei, one that you're interested in that you don't know much about, and one that's really boring that you know a lot about, and smash them together and see what happens. And you can put in a lot of information about this one that you know is reliable, and then in order to get agreement with experiment, you have to study the properties of the unknown nucleus, and that gives you information about it.